Okay, all right. So let me remind you what we've been doing. That's areas between curves that look like, here they are, areas between curves. So remember, so far we've gotten areas by doing the top function minus the bottom function and putting an integral between the two. Because an integral we've seen can get us the area under a curve. Okay, and so we've done functions where we're given the graph, functions where we're supposed to graph, functions that intersect in more than one place. So we have to split up the integral. Left side the blue minus red, but then the right side is a red minus blue. We saw that. We saw one where we had to make the graph like that, pink minus black, and then black minus pink. This is the last thing we did. But so far, it's just all we've done is top minus bottom type of stuff. Okay. Now, here's an example that can show you why that might be limiting or like a little bit annoying. If I wanted to get, look, the graphs of f and g are below, determine the area between, or sorry, enclosed by these graphs and the x-axis. Okay. So the annoying thing here is that, look, okay, I could get the area under this graph. Boop, 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 boop. So far I'm looking good, so far I'm looking good. But then halfway through it kind of switches. So now it's no longer the area under this red graph. It's now the area under this orange graph. And so I can get it, but I have to do two different things. I have to do an integral up to 4, because that's the red graph, and then an integral from 4 on to get the orange graph. And so that's why this might be a little bit annoying. There is a way to fix this so that you can just do one single integral, and that's what we'll learn next. But for now, let's just do what we know. Let's set up an integral that would get this area. So that would be, okay, integral from, well, okay, I got to do this part first for the red graph. That would be from 0 to 4. Out of these two, do you guys know which one's the red one, the curved one? Okay, good. Yeah, this should be the first one, because that's the curved one. This one's a straight line, so that should be a linear function. Nice. Okay, so there's this area so far. And then now I have to add on the area we're missing. So integral from 4 to 8 of this other function, -1/2 x. Okay. Do you see why I had to split it up into two different things? Why I'm adding the two? Okay. All right. So that's kind of an annoying thing, like I keep saying. Have to split it up into two things. If I were to evaluate all these, well, let's just do it fast. Antiderivative of square root of x would be 2/3 x to the 3/2. Remember, because this is x to the 1/2, so you add 1, etc. Okay, and then you plug in 4 and 0. Okay, we've done this a lot, that's why I'm going fast. Then plus, this one would be x squared over 2, but then times another 1/2 would be -1/4 x to the 2nd, sorry. Plus, and then this one would have an antiderivative of 4x. And I'm plugging in 8 and 4. Okay. So now if we plug in our stuff, let's try that. 4 into here would be 4 to the 3/2, which if you don't remember what that means take the square root of it because of the 2 down here. That would be 2. Then cube it. That would be 8. And then times 2/3 would be 16/3. Okay, that's me plugging in 4. Then if I plug in 0, I just get 0. Okay, so I'm not even going to write that. So this part is done, plus this part. Oh boy. Okay, well, 8 squared is 64. Then divided by 4 is what? 16? Okay, so minus 16. 8 times this is 32. There's me plugging in 8. Minus me plugging in 4 would be 16, but then over 4 is -4. And 4 times 4 is 16. All right, nice. And then I'm running out of room, so if you were to simplify all those things and combine all those numbers together, you end up with 28 thirds. Nice. Okay, now let me remind you that this was annoying because we had to split it into two integrals. Is there any way to do it as one integral? The answer is yes. There's an ingenious way to do it where you don't have to change this or write this. It's just an intro to what we're about to do. Where instead of getting areas between these and the x-axis, we could get the areas between these functions and the y-axis. And then good things happen. Watch this. Okay, area between this line and the y-axis would look something like this. Okay, and then if I subtract off the area between the red and the y-axis, that would be me subtracting off this area. So that what we're left with is the area we wanted. And that way we only do one integral. And then if you're thinking, okay, how would I end up getting the area between these things? You just integrate, instead of dx with respect to x, you integrate with respect to y along the y-axis. So you go from 0 to 2 of right minus left, and you'd end up with the area you want. This is kind of a neat thing. So that's what this next section is all about, or this next few examples. Okay, all the examples have used vertical. Like I said, we're getting vertical areas, but now we'll be using horizontal areas, which is a little bit nicer. And like I just said, instead of now going from top minus bottom, like we've been doing, function on top minus function on the bottom, we'll be doing the function on the right minus the function on the left, like I just showed you. All of this will make more sense once we do an example, but just so you're ready for it. Okay, so here's an example. Get the area enclosed between the graphs. So get this area. Okay. So let me show you why this would be annoying to do with respect to x, like vertically. If I were to get this vertically, look what happens. Halfway through, or like right at 2, let me make that a better line. Right at 2, if you were getting top minus bottom function, you end up with an annoying thing because now your top function is this sideways parabola, but the bottom function is also a sideways parabola, so you have to split it up and make it like half of a sideways parabola minus the bottom half of the sideways parabola, and it's just a mess, and you don't want to deal with that. But if you do it horizontally, if you do the area with respect to y, then look what happens. You would be getting the area under this parabola, or sorry, the area between this parabola and the y-axis would look something like this. And then this. And then if you subtract off the area between the line and the y-axis, you end up with something like this, taking all of this off. And look what you're left with is the area you want. This part's a little weird because of negatives, but it does end up working like we want. So what I'm saying is it's much easier to do it horizontally than to do it vertically. So do it with respect to y instead of with respect to x. Okay, so how would we do that? Let's check. All right, so it looks like I should be getting areas from here to here with respect to y. So, okay, here's kind of a tricky question. Do you guys know from where to where I should be going? Where to where I should be setting up my integral? Again, with respect to y. Yes, okay, really good. I'm glad you didn't say so. So the temptation is to go from -1 to 2, but you got to be really careful because those are x values. Instead, you should be going from -2 up to 1. You're looking at y values now. So -2 up to 1, again, because we're going up the y-axis. And then we're doing the right minus the left. The farther from the axis minus the closer. So which out of these functions, which one is the right function? Just to make sure. What's up? Yeah, the parabola. That should be the y² one. Okay, good. Okay, so the right function is this 3 minus y² minus the straight line would be y plus 1. All right, cool. You see why I'm doing it dy? Did that make sense? Why we're doing it horizontally? It's much easier. Okay, all right, and then you just do it the same way. Like now pretend there's x's in there. Like don't worry about the letter. The process is still all the same. So it's still -2 to 1. 3 minus 1 is 2 minus y², and then minus the y. Then, like I said, the process is the same. So the antiderivative of 2 with respect to y is 2y. The antiderivative of that with respect to y is y³ over 3. And then y² over 2, and I'm plugging in 1 and -2. Okay. All right. And then this one's not too bad. Let's just do it by hand. Watch this. Plugging in 1, I would get 2 times 1 is 2. 1³ is 1 over 3. 1² is 1 over 2. Okay, minus, there's me plugging in 1. Now minus me plugging in 2 would be 2 times -2 is -4. -2³ is -8 over 3. And that was minus a -8, so plus 8 over 3. And then -2 squared is 4, so minus 4 over 2 would be -2. All right, cool. And now you have to deal with fractions and everything, but it's not too bad. Let me do it in this way. Watch this. 2 plus 4 plus 2 would be 8, because 2 plus 4 is 6, plus another 2 is 8. Then minus a third, minus a half, I'll deal with those later. Actually, no, let me do this. Watch this. -1/3 minus 8 more thirds would be minus 9/3 for these two guys. But then 9/3 is just 3, so minus 3. And now I have dealt with this, dealt with that, dealt with that, dealt with this, dealt with this. So then just minus the 1/2. So this would be 8 minus 3 minus a half. 5 minus a half, which is 4.5. So 4.5. Or 9/2 if you like that better. Okay, all right. But, the only new thing was setting it up with respect to y. And hopefully this makes sense, but it is kind of a new thing, so if you're confused, ask now. Okay, then the next one is very, very, very similar. It even gives you the graphs. So you guys see if you can figure this out. Take a few minutes. I'll walk around, answer your question. How do you get the yeah, okay, so maybe you're looking in the right places, but just slightly less. You should be looking at where they intersect each other. How the here, what about the cheek? Nice. Okay. Yeah. Try to see what you want to do. Yeah. Big nice. So nice, except small thing. You did parabola minus line, but the farther from the line, farther from the y-axis is the line. So short answer is it should always be right minus line. So you shouldn't. What I was gonna say though is that it wouldn't have mattered that much. You would have just gotten the negative version of the answer and then just positive, but to be fully correct, yeah, it should be right minus that. You did line minus that from negative 2 to oh, is there a 1? Negative 2.
Oh.
Okay, sorry. You were just okay, sweet. Then you're good. Nice. What did you guys do? Someone else did this.
Weird because yeah, it's that minus the travel.
Right. I agree with that part. The small thing I don't agree with is you said your balance should be from 0 to 4, which I know why you said that. You're looking at that side. Okay, thanks.
Maybe negative 1 and 2 or negative.
Yeah, a lot of people do that. All right, I'm going to start writing the answer because I'm seeing a lot of people getting there. I'm going to let you guys do all the work. And then I'll write the answer in a second, like the final number answer. Okay, if you're not done and you don't want to know, then don't look up yet. But the answer's on there if you need it. I didn't show all the anti-differentiation or anything, because from what I saw, most people were doing it right anyway. So if you anti-differentiated everything and plugged in your numbers right and combined all the fractions and everything, you should end up with a final answer of 9/2, or 4.5. Okay, good work. Now, I do want to just do the intro to the next section so that you guys are ready for me to start next time I see you. Okay. Intro to the next section. Actually, I just thought of a better intro to start with. Let me get this on the video. But look how limited you guys are in terms of volumes. You guys think, oh, we've been taught all the volumes. But what if I asked you to get the volume of this trash can? You would be like, oh, actually, I don't know. Even though, I mean, you're thinking, yeah, actually, I do know, but it's not a cylinder because it looks like this. It like goes in on itself a little bit. Do you see? So notice you don't actually know the volume of something very, very, very basic, which you should be ashamed of. But now you don't have to be ashamed of yourself, because with calculus, it's a little bit, you could get the volume of this. So let me introduce it in a simpler way. This is not essential. The next part is essential. I brought with me a ream of paper. This is for the people on the video. And if I wanted to know how much space this ream of paper took up, like the volume of it, then there's two easy ways to do it. I could just do length times width times height, and obviously that would tell me the volume. Or a more complicated way to do it might be to get the volume of this tiny sheet of paper. So let me put this down. So I could get length times width times a tiny, tiny thickness, get that volume. Then get this volume in the same way. Then the next piece, and the next piece, and the next piece, and do that 500 times and add those volumes together. And that would also get me the volume of this entire thing. And that would be a stupid way to do it because it's much easier to do this. But for like the trash can, which we don't know the formula for, we could get the volume of, cut this into a bunch of pieces, boop, 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 get a bunch of, well, what shape would that make? If I were to cut this. Yeah, it would make a bunch of circles. Get the volume of those tiny, tiny circles with a tiny thickness, so technically they're tiny cylinders. Get the volume of all those, add them all together, and that would give me the volume of this. Okay, all right, okay. Does this idea sound like anything I've taught to you before? Adding a bunch of stuff together to get a final, like accumulating a bunch of tiny shapes? Yeah, they sound like a Riemann sum. They sound like an integral. What we've done with integrals, you don't have to write this down yet. I'm going to write the volume thing in a second. But what we've done with integrals is to get the area under here, I took a bunch of tiny rectangles and accumulated them all together, and that gave me the area under here. Now we're going to do the same thing, but with 3D objects. Okay, so the intro notes are what I said. If I wanted. Now you could write this or not. This is really more of a conceptual thing. Like if you think you'll remember this, okay, you don't have to write this. But I think it's neat, so I will write it. If I wanted to get volume of ream of paper here's a picture of a ream of paper. I could use length times width times height, or I could get volume of each sheet of paper and add it all together. So that would look something like length times width times tiny thickness. Okay. All right, now remember when we were doing Riemann sums, that tiny width of each little rectangle, we called that, well, that's what the dx stands for. That's what it represents. It's the tiny, tiny width of each rectangle. So that's what I'll call this tiny, tiny thickness. I'll just call it dx. Okay? And then I'll say that this idea of adding infinitely many or like a ton of tiny shapes should sound a lot like this should sound like an integral. Because, like I said, I'm accumulating a bunch of shapes with a tiny dimension to add together and get one bigger shape. Okay, now let me just address what I would have been thinking in my calculus classroom. I remember when it came to this section, and I was like, wait, how are we about to get volumes with integrals? In my head, this integral, like this symbol was like an area getter. But let me address that right now. And this is not an area getter. This is an accumulator of whatever you put inside. Accumulator. Okay, so what I mean is, so far we've gotten areas with this as a result of it being an accumulator. So let me illustrate what I mean. If I wanted the area under this curve, like, I don't know, whatever this curve is, f of x, then what I'm doing is I'm accumulating this y value with a tiny thickness, so f of x times dx. Then this y value, f of x, times a tiny thickness, dx. Then this y value with a tiny thickness, f of x dx, f of x dx, f of x dx. A bunch of tiny thickness y values. I'm accumulating a bunch of y values, and that's what I'm thinking of f of x as. And then as a result, I get the area under there. But if instead of thinking of these as y values, if instead of putting y values into here, I put in, here, let me just say some stuff. That would be the integral from a to b of y value times tiny thickness would get me the area under there. But if instead I accumulated, instead of y values, I accumulated a bunch of squares with a tiny thickness, or a bunch of rectangles with a tiny thickness, if instead I accumulate from, like, for example, 0 to 3, a bunch of rectangles. This is obviously very informal. Don't ever write this on the AP test. This is just a conceptual thing. But if I, instead of putting y values squares, then this would accumulate a bunch of squares with a tiny thickness. Then what I would get is a 3-inch long little square with a thickness of 3. This would get me an accumulation of these that is 3 inches tall. That's a terrible little box, but that's what that would make. Conceptually, like, that's kind of mathematical, but conceptually, it would get me this. I'm accumulating a bunch of these up to 3 inches, so I get this ream of paper. Okay, and that was the intro I wanted to give. That's where I stopped with my last class. But you'll see how this is used in actual examples tomorrow. It's kind of a wild thing. It's an interesting thing. All right, that's what I've got. Yeah, Taeyong, what's up?
Oh,
Okay.